All right, in chapter 3, topic number 2, what we're gonna be talking about will be, we will still be talking about differentiation, um, but we're going to go over some basic rules, and rate of change. When the main role of the the basic rules is to simplify the work of the definition of differentiation that we went over in topic 1, where we define the differentiation, differentiability. We talked about when a function is differentiable. We talked about the difference between differentiability and continuity and their connection. We also emphasized on the fact that the the, the the derivative of a function is the slope of the tangent line at a given point, or if it's the derivative function, then it's the the slope of any tangent line at any point x given. Now let's start with the constant rule. The constant rule says that the derivative of a function that is constant is always zero. So if I calculate the derivative of a function c with respect to x, as you can see, there is no x involved in this expression c. So there is no x involved in the expression c, but I'm still calculating the derivative of this expression c with respect to x. So if there is no x and I'm calculating the derivative with respect to x, the derivative is 0. So I'm trying to say here is if the variable that I'm calculating the derivative at, or the with respect to, is not included in the actual function that I'm calculating the derivative, then the derivative is 0. That's the constant rule. Here are some examples. Y equals 7, where y is a function of x. Now I want to calculate the derivative of y with respect to x of 7. So that's going to be d7 over dx, which means derivative of 7 with respect to x, that equals 0. F of x equals 0. 0 is also a constant. Well, if I need to calculate the derivative of f, which would be f prime of x, we talked about all the notation of the derivatives, then it's going to be 0. S of t, which is usually the notation of the position of a particle, S of t equals -3. So S of t is constant. The variable is t. Now the derivative of s with respect to t, which is s prime of t, or ds over dt, the fact that the expression that is -3 does not have t, which, or you can say independent from t, then this would be d -3 over dt, no t involved, so that's 0. Here also, y is a function, let's say function of x. Well, they already told me that k is a constant. That's the only unknown factor that we know, what we see here, because pi is a constant. It's 3.14 and keep going with numbers. And when you square it, it still remain a constant. And they tell me that k is also a constant. Now, if I say that y is a function of x, that means with respect to x, k pi squared is constant. So which means the derivative of y, which is dy over dx, derivative of y with respect to x, would be d k pi squared over dx, because I mentioned how y is a function of x, and with no x involved in the expression, this is 0. Application of the constant rule is what? Whenever I'm calculating the derivative with respect to something that is not included in my expression, that means I'm deriving a constant expression with respect to my variable, then that is going to be 0. Next rule is the power rule. The power rule says if n is a rational number, n is a rational number can be a natural number, any fraction, that can be any decimal number, that can be any any number that real number, not real number, that can be any real number actually, but that can also be any fraction, any decimal, any natural number, positive or negative. So n is that, and then I define a function f of x equals x to the power n. F of x equals x to the power n. It's differentiable, and it's differentiable. Remember the definition of differentiability, right? And when I say it's differentiable, that means the limit as x approaches c, or delta x approaches 0, of f of x plus delta x minus f of x divided by delta x exists, right? So that's what that means when we say f of x is differentiable. The limit of f of x plus delta x minus f of x divided by delta x as delta x approaches 0 exists. That's what that means. Well, what I want you to know from that is really that if I'm calculating the derivative of f of x, that is x to the nth power, here is what is it. It's the n bringing down bring down the n as the coefficient of the x, exponent n minus 1. Let me give you a quick example of that. Because when I give you n, x, and n minus 1, that's crazy, right? So if I'm looking for, based on the power rule, if I'm looking for the derivative of x to the power 5, what should I do? That is going to be bringing down the 5. So that's 5 x to the power n. Well, not n, actually. We know it's 5. 5 minus 1. So the derivative of x to the power 5 is just 5x to the 4th. Hope that makes sense. What is the derivative of x to the power 7? Same thing. So that is 7x to the power 6. That's the power. So let's do some examples. What's the derivative? If I have f of x, a function that is x to the power 3, f prime of x would be 3x to the 2nd. Now here is what I have. Cube root of x to the power cube root of x, just cube root of x. Now, if you remember, x to the power n over p over n is the same as nth root of x to the p power. Now look at this. I can go from a rational exponent to a radical form anytime I want. And you're gonna need to do that all the time when you are calculating derivative and when you want to use the power rule. If I give you a radical form, all you want to think of is to transform this radical form into exponent so you can use the power rule. So this cube root of x to the power 1, if you want, there's a power 1 right here, but power 1 we don't need to put it, it's automatically going to be x to the power 1 over 3 because the p in this formula that I talked about is just 1. So the 1 goes on top and the index of the radical goes as the denominator of the exponent. So x to the power 1/3. Well, I'm going to use the power rule, which is x to the power. Well, actually, bring down the power, which is 1/3, right? And then x to the power 1/3 minus 1, always minus 1, right? So 1/3 to the minus 1 equals negative 2/3. So that equals 1/3 x to the power negative 2/3. Negative exponent is a fraction, just 1 over the thing with positive exponent. This is going to be 1 over 3 times 1 over 1/3, the 1/3 that you had, right? It's 1 over 3, and then x to the power 2/3. Now, exponent 2/3, look at this. You can write it as a radical again. I always want you to go to the previous format of your expression. You had a radical, give it as a radical at the end of the expression. So this is going to be 1 over 3 radical, the index is 3, and then x to the power 2, x to the power 2. So this is g prime of x. This is g prime of x. All right. Now let's see this last example. That is exponent 2, but we have a fraction, right? Now, whenever you have a fraction, if you want to feel more comfortable with the If you feel more comfortable with something that is not fraction, it's just 1 over. With an exponent, you can just transform it as a negative exponent. So this is automatically, or can be written as, x to the power negative 2. That's the same thing. Well, if we apply the power rule, that's going to be negative 2x to the power negative 2 minus 1. So that equals negative 2x to the power negative 3. Or negative 2 over x to the third. So that's the derivative of 1 over x to the third, x to the second. 1 y equals 1 over x to the second. The derivative is negative 2 over x to the third power. All right, let's move on to this other rule, that is the constant multiple rule. The constant multiple rule, what does it say? It tells me that if f of x if f is a differentiable function and a constant c is a real number, then c multiplied by f is also differentiable. And then we can find, once a function is differentiable, we can find its derivative. If a function is differentiable, then you can find its derivative. The derivative of cf of x is c f prime of x. Or all you want to do is that, okay, if this function is differentiable, then I can bring the c to the outside and then calculate the actual derivative of the function and multiply the result by c. All right, now let's go ahead and do some examples. 2 over x is the same as 2x to the negative 1 power. Negative 1 power, we can use the power rule to solve it. I'm going to keep the 2, and then I'm going to derive the x to the power negative 1. Or differentiate the x to the power negative 1. Bring the negative 1 down, x to the power negative 1 minus 1. It's always going to be minus 1. So that's negative 2x to the negative 2 power. Or equals negative 2 over x squared. Because power negative, bring down, changes the power to the positive. So this is what? That's like 4/5 t squared. Well, 4/5 is the coefficient c, and t squared, what we do? It just bring the power down, minus 1. So that's 4/5 times 2 t 2 minus 1, which is 8/5 t. 8/5 t. You have a radical right here. Write it as an exponent. So that's 2 x to the power 1/2. X to the power 1/2. Now, we know the 2 is the c for you in this case. Bring the power down, that's going to be the 2 times 1/2 x, 1/2 minus 1. It's always minus 1. So 2 times 1/2 is 1, just that's x to the power negative 1/2. But once you see negative 1/2, it's like there is a 1 over the expression with a positive exponent, 1 over x to the 1/2 power. 1/2 power is the radical, so that's going to be 1 over radical x. Okay. that you getting it? Now, what is that? That's y to the power. That's y equals 1 over 2 cube root of x squared. Now, I don't want to see the radical. I want to see all radical turning into some type of exponent, and then the coefficient I want it to be out, and then solve the problem just like I solve the power with the power rule, and the coefficient is outside until I solve it. So that's gonna be 1/2 1 over x to the power 2/3. Right? So instead, I can also write this as 1/2 1 over, not even 1 over. 1 over is a negative exponent, so x to the power negative 2/3. So that's what I have. So the 1/2 is my coefficient, and I'm gonna use power rule for this part. So that's 1/2 times power will bring the power down 2/3 x to the power negative 2/3. That's not 2/3, negative 2/3, and minus 1. And then simplify this. That 2 cancels out, so negative 1/3 x to the power negative 2/3 minus 1. That's negative 5/3. But I don't want to keep any negative exponent and rational exponent. So I'm going to transform this, the rational exponent as a radical and the negative exponent as a fraction. So that will take me to negative 1/3 1 over the cube root of x to the 5th. I need to simplify this more, because whenever the exponent under the radical is greater than the index, you can simplify this expression. How many times 3 goes into 5? 2 times or 1 time? 1 time. So that's going to be negative 1 over 3x cube root of x squared. So because x to the 5th equals x3 times x squared, and if I take the cube root of this, that's a cube root of x cubed times cube root of x squared. Cube root of x cubed is x, and then times cube root of x squared. So that's what gives me this answer. So this is y prime. This is y prime. So now what I want you to understand from this example is that most of the time when calculating derivative, you might want to rewrite your expression in a format that you know, in order to get the result that you want. So that's why you see that I include this step, this one step here, about rewriting your expression probably in a exponent form, and then you would want to differentiate your expression and then simplify. So those steps would be some outside steps that you do on your scratch paper or whatever, and then get your answers in order. So let's see what this is about. So first, I have this function, y equals 5 over 2x to the third. Now, I already see that the 5 halves is my coefficient. I'm going to rewrite it as 5 halves. And then there would be some type of 1 over x to the third. But I want something in power 5 halves. I want something in power, just power, can be positive or negative, so that I can use the power rule. So 1 over x to the third is like x exponent negative 3. So now that's the same expression rewritten in a different form that would allow me to proceed with the differentiation. Well, I can use power rule, but I know the coefficient 5 halves would not change, because that's pretty much what is it if I use the multiple factor rule, the constant multiple rule. So then that I can use the power rule for this part, bring down the power times negative 3, and then x to the power negative 3 minus 1. And then simplification would be negative 15 over 2 x to the power negative 4. See, that's those are the steps you want to take in order to get your answer. Let's try this one, the next one. Rewrite. So that's a 5 over 2 to the power 3, because when I have a times b to the power n, it's like a exponent n times b exponent n. That's why the 3 here is the power of 2 and also the power of x. So basically this is 5 to the power 8. So that's 5 to the power, 5 over 8, not 5 to the power 8. It's 5 over 2 to the power 3, but 2 to the power 3 is 8, so 5 over 8. And then x times 1 over x to the power 3, right? Which is x to the power negative 3. Right, so then now we can go ahead and perform the differentiation of 5/8 times x to the power negative 3, which is the 5/8 will not change. And then we will bring down the power negative 3, x to the power negative 3 minus 1. So that is negative 15 over 8 x to the power negative 4. Okay, let's move on to the next example. Next example will be the rewritten expression is 7 over 3 x to the power negative 3, negative 2 in denominator would move up to be x to the power 2. So I have it. I can use the power rule in the constant multiple rule. 7 over 3 times 2 x to the power 2 minus 1. Simplify. That's 14 over 3 x to the power 1, but just x to the power 1. We don't have to write it. So that's 7 over So that would be 7 over 3 to the power negative 2 x to the power negative 2. And then if we move x to the power negative 2 up and negative 3 to the power negative 2 up, so that would be 7 3 to the times 3 to the power negative to the power 2, 7 times 9 times x squared. 7 times 9 is 63. So that's 63 x to the power 2. And then, so that's the power form, and that's the expression rewritten. And then now we can use the power rule to derive this or differentiate this. So that's 63 times 2 x to the power 2 minus 1. 63 times 2 is 126 x to the power 1, so just x. So now let's talk about the sum and difference rule. The sum and difference rule is that if you have two functions, f and g, and then if f of x and g of x are two differentiable functions, then the sum f plus g is differentiable, and f minus g also is differentiable. And the derivative of f plus g with respect to x is f prime plus g prime, or the derivative of f minus g with respect to x is f of x minus g of x. Well, that takes me to calculating the derivative of terms of a polynomial, right? So for this one, I would use the power rule. For this one, I would use the power rule. And for this, for this one, the first one, I would use the power rule. For the second one here, I would use both the power rule and the power rule and the constant multiple rule. And then for the last one, I would use the constant rule. So the power rule will give me 3x to the second power. 3 minus 1 is 2. And for the second one, it will be minus 4 times 1x, 1 minus 1. And then the other one will be plus 0 because it's a constant rule. The derivative of a constant is 0. So I would say that this is not needed. And x exponent negative 1 minus 1 is x exponent 0, which is 1. So 1 times 1 is 1. And then that is negative 4. So derivative is 3x squared minus 4. Okay, next example. I have negative x to the 4th over 2 plus 3x to the 3rd minus 2x. So we would do the same thing as the previous example. So that's negative 1/2 x to the 4th plus 3x to the 3rd minus 2x. Bring down the exponent, so that's negative 4 over 2, x 4 minus 1 plus 3 times 3x, 3 minus 1. negative 2x, negative 2 times exponent 1, right? So that's 1x 1 minus 1. So that will be negative 4 over 2, that's negative 2x third, x to the third, plus 9x squared minus 2. So the derivative of this expression or function is negative 2x to the third, x to the third, plus 9x squared minus 2. And then let's see the next example here. We can divide by x. So this is y equals 3x plus 3 plus x exponent negative 1. Because I divide by x here, that's cancel 1x. That gives me x, 3x. Divide here, x gets canceled. And then 1 over x is x exponent negative 1. So that's how I get this. So I have this. Then let's go ahead and find the derivative. So this one would be just 3. This one, the derivative of this would be 0. And the derivative of the last term would be plus negative 1x, negative 1 minus 1. So that's 3x, 3 plus minus x to the negative 2 power, or that's 3 minus 1 over x squared. So that's 3 minus 1 over x squared. And then remember how I said when you have radicals, you need to chase it by make sure that you transform it into a power. So this would be f of t equals x to the power 1/2 minus 6 t to the power 1/3 plus 7, right? So let's do the power rule for each term. 1/2 x negative for f prime of x of t, x prime of t, that is 1/2, that's t, sorry. So that's 1/2 minus 1 minus 6 times 1/3 t to the power 1/3 minus 1 plus 0, right? So that equals 1/2 t to the power negative 1/2 minus 2 t to the power negative 2/2, negative 2/3. So that is 1 over 2 square root of t minus 2 over square root of cube root of t squared. So that is 1 over 2 square root of t minus 2 over cube root of t squared. So that is that are the step-by-step examples for this. Now we're gonna go ahead, look at the derivative of sine and cosine, sine, cosine, and exponential functions. So the derivative of sine x with respect to x is cosine x. And the derivative of cosine x with respect to x is negative x. Well, Those are things that we're going to be talking about later, but that's what you need to know. You need to know that the derivative of sine x with respect to x is cosine x, and the derivative of cosine x with respect to x is negative sine x. So knowing this, derivative of cosine x with respect to x is negative x, negative sine x, and the derivative of sine x with respect to x is cosine x. And then we know that the derivative, we know also that the constant multiple rule, you can just keep the constant out and then derive the actual function, multiply it by the constant. So that will take me to 2 here, and then derivative of cosine x of sine x is cosine x. So that is cosine x. That's the derivative of 2 sine x. Derivative of 2 sine x is 2 cosine x. Easy, right? So here's what we have here. Sine x divided by 2, it's like 1/2 of sine x. We write this. So that's basically going to be the same scenario here. Keep the 1/2 and then derive the sine x to cosine x. So 1/2 cosine x. What's the derivative of that? What's the derivative of x? Use the power rule. Power is 1, bring it down 1, and then 1 minus 1 is 0. So x exponent 0 is 1, so that's 1 times 1, so that's just 1. Derivative of x is always going to be 1. And then plus, what's the derivative of cosine x? Derivative of cosine x is negative sine x. This you need to know it. So that's negative sine x. So basically it's just 1 minus sine x. Okay, so let's see this. Derivative of cosine x. Derivative of cosine x, go back here, is negative sine x. Negative sine x. Derivative of sine x, that's a constant. Just bring it. Negative pi over 3. And then derivative of sine x is cosine x. So that's cosine x. So that's it for this. Now let's see derivative of the exponential function. Well, that's the easiest thing you can ever face. Derivative of exponential of x with respect to x is itself. E to the x derivative, its derivative is itself. Now, if we apply the constant multiple rule, that would give me f prime of x here is 3 exponential x, because it's the thing is its derivative. So that's the derivative. For this one, power rule, f prime of x is 2x plus e to the x. This is exponential x minus, but the sine x. Go back to this. Sine x, derivative of sine x is cosine x. So then that's going to be f prime of x equals cosine x minus e to the x. So that's the derivative. Derivative is easy. It's just like we need to understand the steps. All right, here is another example. Find A and B such that f is differentiable everywhere. So f is differentiable everywhere. That means this function is differentiable for all x less than 0, and this function is differentiable for all x less than, greater than, or equal to 0. Now, so the function here is differentiable in all points, everywhere. Now, the only question is, what is it at x equals 0? Because we have two common functions. One is in for x less than 0, and one is for x greater or equal to 0. And all these, they are, even all real numbers, they will be continuous. So I would say differentiable, I mean, cosine x is differentiable at all real numbers so it's differentiable over negative infinity to 0, right? Because it's open for this. And then ax plus b linear is differentiable at all real numbers. Thus, it's differentiable over bracket 0 infinity. Now, the only problem is, what is it for 0? Because the first portion of the function, the first part of the function is not quite sure. We're not quite sure whether it's differentiable at 0. Now, that's what we're going to learn. Now, let's discuss the differentiability at x equals 0. So we need to make sure that we calculate f prime of 0 plus, it should be f the same as f prime of 0 minus, right? These two must be the same. So f prime of 0 plus, what is it? It's 0 plus, right? Let me start with the 0 minus, because that's the top function. So that's plus 0, 0 plus 0 minus. It's cosine x minus cosine 0 over x minus 0. and then f prime of 0 plus is a x, actually a times 0 plus b that's a x plus b minus a times 0 plus b over a minus 0, which is just a. So basically, I missed this. That's limit as x approaches 0 of this, and then that's limit as x approaches 0 of this. That will give me this. And then we expect these two to be the same. So it's the expectation of them to be the same. So basically, that's limit as x approaches 0 of cosine x minus 1, cosine 0 is 1 over x, which is 0, the special limits. And then this will be that's 0, b minus b, that's also 0, that's a over a, so that's limit as x approaches 0 of just x, which is 0. So okay, so there was a mistake here. We're gonna fix it. So basically, that was not an a. That should be x, because that's x minus 0. X minus 0 is x. So we would have a times 0, that's 0. That's a 0. And then b minus b, this minus sign changes this to a minus. So b minus b is 0. So I'm gonna have ax over x, x cancels, so that's a. And the limit, a being a constant, a minus limit as x approaches 0 of a is gonna be a. So that means if f prime of 0 plus minus is the same as f prime of 0 plus, that means 0 equals a, so a equals 0. And in this case, this condition is sufficient for us to have the result that the function is differentiable. And that makes b can be any real number. B can be any real number. B can be any real number. So we're gonna cover the rate of change in class with the lesson that we previously intended to cover in class. So we're not going to cover rate of change in this video. And then if any question that you may have concerning this lesson, I know in video it's not the perfect format to cover a lesson. So we would answer those questions prior to the test, or I will be available in my office hours to answer any questions you may have. All right. So that conclude this lesson.